Hello, today we're going to be looking at solving some systems of three equations. Be prepared to pause the video if you need to. I may go through it kind of quickly, but I want to give you a few examples of how you would go through problems like this. So this first one here, we've got three equations with three variables. We've got an x, a y, and a z, and we want to solve for each of those variables. Now, in a graphical mindset, we're basically determining where three planes would intersect. When we look at this, the easiest method to use is going to be elimination. And it doesn't matter which variable we eliminate first. We could eliminate our x's first, or our y's, or our z's. Usually it's just going to depend on which one looks like it would be the easiest to eliminate. So for example, we have a 2x, a 6x, and a 2x. We could multiply the top equation by a -3. That would give us a -6x, and the bottom equation we could do the same thing, but maybe it's easier to get rid of the y's here. We already have a +3y, and then we have two equations that both have a -3y. So the first thing that I'm going to do is I'm actually going to just kind of number these two equations here, or these three equations, excuse me. So I'm going to number this equation with a 1, this equation with a 2, and this equation with a 3. And so the first thing that I'm going to do is I'm going to combine equations 1 and 2. And I'm going to use elimination. Since the y values will already cancel, I can just add the two equations together. So a 2x plus 6x gives us 8x. The y's cancel each other out. A 3z plus a 4z gives us 7z. And a 6 plus a 12 gives us an 18. So we've just combined to get rid of our y values in equations 1 and 2. But notice we still have an x and a z, which means we have to get rid of y values in another set of equations. And since we have a +3 in the first one and a -3 in the third one, we'll combine 1 and 3. So if I combine 1 and 3, 2x and 2x gives me 4x. The y's cancel. 3z and 2z gives me 5z. And then 6 and 6 gives me 12. So I've used elimination twice to get it down to two equations with two variables. Now I need to get rid of either my x's or my z's next. And we can see that getting rid of the z's is kind of difficult. 5 doesn't go into 7, but 4 does go into 8 over here, so we can get rid of the x's first. In order to do that, I'm going to have to multiply my bottom equation by a -2. So that gives me -8x minus 10z equals -24. Now I can combine these two equations. Okay, whoops, excuse me. That will get rid of my x values. 8x minus 8x, gone. 7z minus 10z gives us a -3z. And 18 and a -24 gives us a -6. So now we just divide by -3, and z equals 2. So we combined our two equations to get it down to one equation with one variable, and now we've solved for that one variable. It's 2. Now we're going to take that answer, we're going to plug it back into either one of these two equations up above to find x. So I'm going to use 4x plus 5 times z, so 5 times 2 equals 12. 5 times 2 is 10. So then if we subtract the 10 over, 4x equals 2, and divide by 4, x equals 2/4 or 1/2. So now we have x and z. We have to go back to the beginning of the problem, plug them in to solve for y. I'm going to use the first equation because that has a positive 3y in it. So 2 times x, 2 times 1/2, plus 3y, plus 3 times z, z was 2, equals 6. So 2 times 1/2 is 1, plus 3y, 3 times 2 is 6. So I get 7 plus 3y equals 6, and then subtract the 7 over. 3y equals -1, and divide by 3. Y equals -1/3. And when I get my final answer, I want to write it as a coordinate. So x was 1/2, y was -1/3, z was 2. Okay. And that's my final answer. So these three planes would intersect at the point 1/2, -1/3, +2. Systems of three equations, or systems of more equations too, has other purposes as well, but this is kind of the context we're going to think of it in for right now. So let me show you another example here. Here we've got a system of three equations. Again, not too difficult to get rid of any of the variables, but if you notice, again, the y values just coincidentally happen to be the easiest again, because we've got a -y and then two equations with positive y's. So if I number these, I could combine 1 and 3. X and 2x, 3x. The y's cancel. 3z and 3z is 6z. And 3 and -7 is -4. And then I can combine 2 and 3. So 2x and 2x is 4x. The y's cancel. 6z and 3z is 9z. And 2 and -7 is -5. Okay. Now, to get rid of my x's or my z's, I'm going to have to multiply both equations this time. Easiest thing to do, you could find smaller numbers to multiply by, but if you just want an easy way out, since this is a 3 and that's a 4, multiply by the opposite. So multiply this one by 4, and we'll multiply this one by 3, but I'm going to make it a -3. That way I'll get a positive 12x for the first one and a negative 12x for the second one. So 3x times 4, 12x, 6z times 4, 24z, and -4 times 4, -16. For the bottom equation, 4x times -3 is -12x. 9z times -3 is -27z. And -5 times -3 is 15. X's cancel. Combine our z's, we get -3z. -16 plus 15 is -1. Divide by -3, and we get z equals 1/3. Okay. Again, go back up to one of these equations, plug it in to solve for x. 3x plus 6 times 1/3 equals -4. 3x plus 2 equals -4. Subtract the 2, 3x equals -6. And divide by 3. X equals -2. Take both of those answers, plug them back in to one of the first three. So x is -2 plus y plus 3z, and z was 1/3, equals 3. So I can add the 2 over. I get y plus 1 equals 5. Subtract the 1 over. Y equals 4. So my answer, x is -2, y is 4, and z is 1/3. Okay. All right. This next one works out kind of interesting because if we look at these first two equations, and if we just subtract equation 1 from equation 2, the x's cancel, the y's cancel, the z's cancel, so we have 0 equals negative 60. Since 0 does not equal negative 60, this one has no solution because we have parallel planes. These first two planes are parallel, just like when you have two equations of lines and the lines are parallel, there is no intersection. So here we have no intersection because the planes are parallel. This one here, again, we could subtract equations 1 and 2, and the x's and y's will cancel. I'm going to do 2 minus 1, so that's z equals, and then 12 minus 12 is 0. I could do the same thing with these two equations, but I've already solved for z. Z equals 0. So if I just plug 0 in for z, every equation becomes 6x plus 4y equals 12. What that means is that these three planes intersect on this line. Okay? There's an entire line where they intersect and not just a single point. So if you ever get just one of your variables to be 0 and then the rest of the equations are the same here, or a variable could be something else, as long as you end up with the rest of the equations all being equal after you plug that variable in, that means they intersect at a line. All right, this one, you can see that it's not quite as easy to solve as any of the other ones. What I would try to do is I would try to just take one of your equations and maybe multiply it a couple of times in this case. So, for example, I'm going to eliminate the z's first this time. I can multiply by 6 to get a 6z, which will eliminate this negative 6z. So that would give me, if I multiply by 6, that would give me negative 12x plus 12y plus 6z equals 30. And then I can multiply, or I can combine it with the top equation. And that gives me negative 7x plus 8y equals 11. Okay. Now if I want to combine it with the bottom equation, I'm going to have to multiply by 5 to cancel out this negative 5z. So if I multiply by 5, I get negative 10x plus 10y plus 5z equals 25. And if I combine it with this bottom equation, I get a negative 7x, a positive 4y, and it equals 9. So now I've got these two equations, and they're going to eliminate each other pretty easily. I'll leave it up to you to finish solving the problem from here, but it should result in an answer of negative 1, 1/2, and 2. So this has been solving systems of 3 equations with 3 variables algebraically using elimination.